This video is about curve sketching with calculus. For our notes, we'll say this: we will do our curve sketching with calculus, but not a calculator. So we're trying to understand all of the concepts of calculus that go into understanding a function all the way to its graph, but we don't want to immediately rely on a calculator to try to just look at the picture. We want to understand all of the attributes and characteristics first. General steps for analyzing and sketching a function can be said as follows. First, we're going to find the first and second derivatives. Secondly, we're going to use the original function f of x to find the domain, symmetry, intercepts, and asymptotes. Now, all of those, with the exception of asymptotes, can be done entirely without calculus. Those are just pre-calculus algebra topics that we'll have to be reviewing as we do this. And then thirdly, we're going to use the first derivative to find intervals of increasing and decreasing. We've already discussed this as it relates to the first derivative with the calculus involved, but also then critical numbers and any local or relative extrema. Fourthly, we'll use the second derivative to find any inflection points and then any concavity or intervals of concavity. And we'll put a note here that says local or relative extrema can be found using the first or second derivative test. That kind of pertains to steps 3 and 4 here. Of course, those two derivative tests involve the first and the second derivative respectively. So often, as we noted when discussing those tests, the first derivative test can be easier because you don't need to find the second derivative to use it. But it's just good to note here that you could technically use either of those tests to find the relative or local extrema. Let's also recall that if the limit as x approaches positive or negative infinity of f of x equals L, then y equals L is a horizontal asymptote. And secondly, if the limit as x approaches a from the right or left of f of x equals plus or minus infinity, then x equals a is a vertical asymptote. So those pertain to the step 2 above where we find asymptotes. And as I mentioned there, that would be one of those attributes that could involve some calculus with these limits, unlike the other ones before, which is just algebra. Let's try an example where we want to analyze and sketch the following function. The function is given as f of x equals the quantity 4 minus x squared in parentheses, all raised to the power of 5. Now, as far as going through each of the steps defined above in these notes, I think there's a convenient way to organize it all. And, there perhaps are other good ways to do this, but one of the main problems in these kinds of problems is simply staying organized. So what I like to do is kind of turn the paper maybe in a landscape fashion, so more wide than it is tall, and then across the top of the paper put a few different columns where we have the original function f of x given, as we have one here, and then in the next column at the top we'll put the first derivative. Now, this video is not meant to describe the process of finding derivatives, so I'm just going to list them here. We've done that plenty of times previously, but any derivative rules we have can be used. That is the shortcut rules. We're not using the limit process for these derivatives here. The first derivative of this function will be a negative 10x times 4 minus x squared all to the power of 4. That's already simplified using the chain rule, as we know by now. And then in the third column, we'll find the second derivative, so f double prime of x. And similarly, that simplified derivative will be 10 times 4 minus x squared in parentheses to the third power times 9x squared minus 4. Again, that's already simplified using the chain rule as applicable. Now, we want to go through, as we noted above, each one of these functions and use them to find what they're good for, which we've listed. So we said above that the original function f of x can be useful for finding the domain. Let's go ahead and do that. Notice this function is just a polynomial function. 4 minus x squared all to the 5th has a domain of all real numbers. There's nowhere that is undefined as could be explored. Now obviously, depending on the example we're doing, we may have to do a little more work to find out if it is undefined somewhere, but this one is simply defined everywhere. We can also use the original function to understand any symmetry it might have in its graph. Of course, symmetry is the whole odd or even aspect of a function, and that can be, as I could review here, found by plugging in f of negative x. In this case, f of negative x equals f of x. That's the definition for an even function. And even function means it has symmetry about the y-axis. Really, the only point of exploring the symmetry is just an aid in graphing at the very end. So we just have to make sure that our graph at the end does indeed have y-axis even symmetry. Next, we'll want to explore any intercepts. As you may recall, to find an x-intercept, you will set y equal to 0, which is also known as f of x. So we could say 0 equals 4 minus x squared to the 5th and try to solve this for x. Of course, this would mean 0 equals 4 minus x squared, which would mean 0 equals plus or minus 2. Sorry, not 0, x equals plus or minus 2 here, which means we have two x-intercepts. They would be negative 2 comma 0 and then positive 2 comma 0. So those points will show up on our x-axis as the x-intercepts. For the y-intercepts, of course, we set x equal to 0. Here, that would be like finding f of 0. If you plug in 0 to this function above, you'll end up with 1024, which means the point 0, comma 1024 will be our y-intercept. Next, we can explore whether our function has any asymptotes. And to do so, we can consider the limits as defined above, or there's a bit of a shortcut algebra to it in this case, or any case. If it's simply a polynomial function, it's not undefined anywhere, which means we're not going to have a vertical asymptote, and the limit as we approach positive or negative infinity as considered for this function is going to be infinity as well, not a real number, which means we actually have no asymptotes for this function. So good to know. That means we won't have any on our graph. Of course, in any function, if you do have asymptotes, those are really helpful to graph along with everything else. Moving on to the first derivative, we first want to start by using it to find any critical numbers. We've discussed these by definition lately, and that would be where either f prime of x is 0 or f prime of x is undefined. We want to explore both of those options. To set it equal to 0, we would just understand negative 10x times 4 minus x squared to the 4th to be equals to 0, or we want to know where would that happen. It would happen a couple different places. That would be either where negative 10x is 0, which would mean x is 0. This is just using the zero product property here. Or for the second factor, which we've already kind of done in looking for these x-intercepts, this would be where x equals plus or minus 2. Now, all of those values are in the domain, which of course is all real numbers here, which means we actually have three critical numbers for this function, 0 and plus or minus 2. Of course, this function is not, or this derivative and this function are not undefined anywhere, which means we get no new critical numbers from that consideration. Now, with our critical numbers, in exploring what they mean for our graph, it's usually good to put them on a number line, as we've seen already. So let's go ahead and get a number line and then plug our, or put our critical numbers of negative 2, 0, and positive 2 kind of in order on the number line. And we want to test around them to find out where this function is increasing or decreasing. And of course, as you recall, we can do so by testing the first derivative at values that are in these intervals. So let's pick something to the left of negative 2, perhaps f prime of negative 3. And we want to pick something really in all of these different intervals. So maybe f prime of negative 1 could happen between negative 2 and 0. Between 0 and 2, we could try f prime of 1. And then, of course, after 2, we could try We could try f prime of 3. And so we're just plugging those inputs into the derivative function defined above. We'll get, I'll just summarize it here, f prime of negative 3 turns out positive. F prime of negative 1 turns out positive as well. F prime of 1 turns out negative, and so does f prime of 3. Given what we understand about the relationship between the sign of the derivative and the increasing, decreasing nature of our function, we could summarize and say it's increasing to the left of negative 2. It's also increasing to between negative 2 and 0. It's decreasing between 0 and 2, and also decreasing after or to the right of positive 2. Alright, now that could also help us understand where any local extrema might occur. So let's start putting all this stuff down. We know it's increasing from negative infinity really all the way up to 0 if we include these intervals. Negative infinity to 0 would be both places it's increasing. Yes, there's a critical number at negative 2, but that does not have to be a place where the increasing or decreasing changes. And so we'll just kind of understand that increasing occurs all the way from negative infinity to 0 here. Similarly, we could say it's decreasing to the right of 0, so we'll say from 0 to positive infinity there. These are open intervals defining these intervals of increasing and decreasing. And then also based on our definition, we know that there's a change from increasing to decreasing surrounding the value 0, and we know that 0 was one of our critical numbers, which means we can say that there is a local max, or you could say local or relative max, at 0. So what is the y-coordinate there? Well, we actually happen to know that already as our y-intercept, so that'd be the point 0, 1024, 0, 1024, and we know that must be a local max really by the first derivative test. If you go back and review what that is, there's a change in the increasing, decreasing around that critical number, which means there must be a local max there. You could employ, as we've said above, the second derivative test also there, but again, we would have to move on to the second derivative to do that, which is fine, but we already have this first derivative set up, which means we know for sure already that this will work. So we can include all of these things as parts or attributes of this function and its graph. Now if we move along to our second derivative, which we've already identified and written above, this is our third column here, we know that this one can be used to search for some things, including the inflection point. Right, so we looked for critical numbers for the first derivative, now we're looking for inflection points. Okay, similarly, as you go back and recall, this would be where the second derivative is either equal to 0. To set our second derivative equal to 0, of course, would mean any of its variable factors could be 0. So we'll take out the 4 minus x squared, that might be 0, or if that's 0, then our second derivative is 0. Of course, we know that happens, that occurs at plus or minus 2. We've already discussed those places. But it also would occur when the second variable factor, the 9x squared minus 4 equals 0. And that would occur when x is equal to plus or minus 2/3. You could factor that or use the square root property to figure out what x should be in that case in those solutions. This means we have some inflection points, and let's go ahead and note them now before we start understanding what's happening around them. And those would be when x is any of these values. We know some of these already, so we could say negative 2, 0, positive 2, 0. Those happen to be some x-intercepts, so we know what those values are. But then also, when we plug in the other values, we'll have negative 2/3, comma, f of whatever that is, and then positive 2/3, comma, f of 2/3. So we're not actually computing those values right now, but we know that's where they would occur. There may be a context in which you would need to label them in exact form or estimated form or rounded form. At this point, we're just kind of understanding where they are. And without a calculator, there won't be a lot of detailed number crunching we're going to do. We want to be able to label and, as needed, maybe get an approximation of where those points may occur on the graph, but we'll just leave them in more the exact or symbolic form at this point. Okay, we know those are the inflection points. Now, we still have to understand what's going on surrounding all this. So again, we'll use a number line, and I'm going to do another number line since one of them would get a little overcrowded. We already have one used for the critical numbers and increasing, decreasing. We want another number line for all these inflection points. I'm going to put the x values surrounding which the concavity may be changing here, which is what we're looking at. So we have -2, -2/3, +2/3, and 2. Those are just the x values from all these inflection points. And we're expecting the concavity to change surrounding them. So we can test that with the second derivative. If I pick f double prime of, let's say, -3, something to the left of 2, that will turn out to be negative, which you could verify with a calculator. And in that way, this means concave down. If you go back to our notes about the second derivative and how it impacts the graph shape, you'll recall when the second derivative is negative, we have concave down. Now, there's not a lot of room left on my space here to write out the detail of the rest of these, but we're going to do the same thing, just plugging in the values in any of these intervals to the second derivative. Now, something between -2 and -2/3, you could pick maybe -1. That'll turn out to be positive, which means we go concave up in the next interval, and this just keeps changing. Concave down, concave up, concave down. We can go ahead and summarize the concavity of this function by just writing it out in interval form. So we could say our function is concave down, really anywhere we've labeled, which would be a few different intervals. So it's the open intervals from -∞ to -2, and then the next one would be -2/3 to +2/3, and then lastly 2 to infinity. So really 3 intervals there. And then we could say it's concave up, and a couple other ones, that'd be all the other ones. So -2 to -2/3, and 2/3 to 2. Okay, so this is all kind of coming in as part of our analysis and solution. Ultimately, this all will show up on our graph, but we're just kind of getting all the main characteristics written down and summarized now so that we have everything we need when we're ready to graph. As we move now to graph everything we've analyzed, it's always good to start with some of the basic structural things such as intercepts, asymptotes. You'll notice or recall above that we do have some intercepts. We'll start by putting those down. Now, they're not something that'll fit nice. We're going to have to adjust our scale here, right? You'll recall our y-intercept was 0, 1024. So we're just going to have to say, okay, that's way up there on the y-axis, but I'm just going to put it there without any actual scale tick markings, because we also know that we had x-intercept at -2 and +2, and there's no way that this would be to scale if I write it out even like this. So we're going to have to just summarize and label things to be clear. You'll also note above that we have some inflection points at -2/3 and +2/3. I'm just putting these kind of, to scale. That'd be somewhere between the positive -2s and 0. Okay, and those were inflection points. Now let me put our x-intercepts in at the positive and -2. Inflection points means the concavity changes there, and you'll recall we've labeled the concavity above. Now, if you go way up above, we also analyzed earlier that this has even symmetry, which means we're expecting it's y-axis symmetry. If I fold this graph over the y-axis, one side should land directly on the other side. It can be helpful now, once the intercepts are plotted, or if there is an asymptote, you'd plot that as well. It can be helpful to put some other key indicators on here just to help shape the graph, such as concavity or increasing and decreasing. So if we go back and recall, we had concave down to the left of -2, then it went concave up, then concave down between -2/3 and +2/3, then concave up again, and then finally concave down again after that. So just slightly labeling the concavity here, maybe in a different color or something, just can help frame the graph up a little bit better. We also noted some intervals of increasing and decreasing. To the left of -2, it was increasing. Between -2 and 0, it was increasing. Between 0 and 2, it was decreasing. And then after 2, it was also decreasing. So putting these little arrow segments on there can be helpful. Again, this is just there to help shape our graph as we draw it. The tricky part can be then now trying to summarize all of this information with some kind of curve that would represent it all. So if it's increasing but concave down to the left of -2, we could maybe imagine it looking something like a curve that's kind of bending upward toward 2. We know it hits at the point -2, 0. We also know eventually it's going to hit up at the y-intercept of 0, 10, 24, but we also know that the concavity changes at -2/3. So we could possibly draw a curve that continues through the point -2, 0, but then all of a sudden changes from concave down to concave up. That can be tricky to identify. It can be tricky to identify visually how that looks, but I'll put a solid green point there where the curve is at -2/3, and at that point the concavity changes from concave down to concave up. Alright, so it can be, again, tricky to draw that, but our curve does somewhat summarize that. It continues concave down, but now that we've drawn really what could be seen as half of the graph, if it's symmetric about the y-axis, we should be able to trace the same kind of graph on the opposite side, still intersecting at the point 2, 0, using the same kind of concavity with the inflection point when x is 2/3, and we'll get some kind of graph that looks as we have it here. So it's kind of a downward shaped, kind of bell, somewhat bell-shaped design using all these attributes. Let's try a second example. This one reads f of x equals 1 plus 1 over x plus 1 over x squared. And like we did before, it's good to summarize the materials we'll be needing, which include the derivatives. So we'll keep our first the original function shown for what we can use it to find. We'll also then, next to it, put our derivative. In this case, y prime would be -1 over x squared minus 2 over x cubed. Okay, again, those are just using some shortcut rules on derivative findings there. And then thirdly, we could say f double prime of x would be, in this case, 2 over x cubed plus 6 over x to the 4th. Okay, so those could all be found. Really, it's a separate problem to find the derivative or second derivative entirely in and of itself, but that's what we should end up with for those. Now, it also can be helpful to write our function with a common denominator. So to take our original function and write it with an LCD, we could say just f of x equals, and then it would turn out to be x squared plus x plus 1 all over x squared. It's helpful because to use that to find the domain and anything else, setting it equal to 0 with a common denominator is just much simpler. So in this case, we'll say our domain is everything except 0. So -infinity to 0, union 0 to positive infinity, using interval notation there. For our symmetry, using that same test of f of -x, this one actually has none, so we're expecting no symmetry with the graph. For our x-intercept, remember that's setting y equal to 0. In fraction form, that'd be like saying the numerator of this function is 0, but x squared plus x plus 1 actually never does equal 0, so there is no place where we have an x-intercept. Okay, fine. That's just good to know. That means we don't have to worry about 1 on our graph. We would be setting x equal to 0 for this y-intercept, but 0 is actually not in the domain, so we can't do that, which means there's no y-intercept either. Okay, so no intercepts. Lastly, we can consider any asymptotes for this original function. Again, you can go back to the limit definitions for these and recall that this would have, using those, a horizontal asymptote at y equals 1 and a vertical asymptote at x equals 0. Now moving along to the first derivative and what we can use it to find. Again, it would be convenient to write it with a common denominator. It's just easier to use it that way. So we could say f prime of x would be negative x minus 2 all over x cubed. That's just getting an LCD of x cubed for those terms. And of course we'll use this first derivative to find any critical numbers. So we'll say here is f prime of x equal to 0, or is f prime of x undefined anywhere. Of course, it could equal 0 if x equals 2, and that is within the domain, which means that is a critical number. This is only undefined at 0, but that's where the original function is undefined, which means we get no new critical numbers from the consideration of when that first derivative is undefined. So we really only have one critical number here, that's when x equals 2. Of course, we'll want to analyze our function surrounding this critical number that we've found of negative 2. But there's an extra little trick here that I'd like to suggest, and that is, if we have a vertical asymptote, which we do in this case, I also like to put that on the number line when we're doing this analysis. It's not a critical number, okay? 0 is not a critical number, but it's helpful to understand what's happening there. We've already understood there to be a vertical asymptote there, so I like to actually write or draw one in this stage of the analysis because it's just helpful to keep in mind. Now, surrounding this critical number of negative 2, of course, we'll want to test the first derivative surrounding it. So we could test, like, f prime of negative 3, perhaps f prime of negative 1. And when we do, we'll find that it's negative to the left of negative 2. So f prime of negative 3 should be negative. F prime of negative 1 should be positive, which is already giving us a hint that we have a local or relative minimum at negative 2. And then to the right of our vertical asymptote, it's good to test the derivative there as well. So let's test f prime of positive 1. We'll find that that's negative, which means it's decreasing there. So again, 0 is the vertical asymptote. It's not a critical number, but as you can see, it still matters in testing where the function is increasing or decreasing, because that can change surrounding an asymptote. And so I like to put it on the line as in this phase of the analysis, just to make sure we're understanding what's going on entirely. So we can say in summary here that our function is increasing simply on the interval from negative 2 to 0. We can say our function is decreasing from negative infinity to negative 2, as well as from 0 to infinity, if we go with these two intervals as described here in our graph above. And then we can, based on the first derivative test, say that we have a local minimum value where this valley occurs. So that'd be at the point negative 2, comma, whatever the function value is there, which I computed to get 3/4. That's just basically computing f of negative 2. So we have a local min there. We have intervals of increasing, decreasing. All of this should show up on our graph when we finally get there. Moving on next to the second derivative, kind of like we've been doing, it's usually helpful to write it with an LCD in place because we'll be looking for places where it's 0. So the LCD would mean that the second derivative, f double prime of x, should be 2x plus 6 all over x to the 4th. That's just getting a common denominator for it. We can search for inflection points by setting f double prime, the second derivative, equal to 0. Remember, inflection points are places about which or surrounding which the concavity changes. And so looking where the second derivative is 0 can help us find those places. Of course, that would be true when x is negative 3. That's just setting the numerator of this second derivative equal to 0, which means we want to analyze what's going on with our function surrounding that. So we'll go ahead and put that value on our number line. But like we did with the first derivative, I think it makes some sense also to put or mark down our vertical asymptote on this same number line, just to keep in mind what's happening there. If we test the sign of the second derivative to the left of negative 3, like f double prime of negative 4, we'll find that that's negative, which means we have concave down to the left of it. And then to the right of that value, like f prime of negative 2, let's say, or negative 1, we'll find that to be positive. F double prime, we're checking the second derivative here for concavity. So the second derivative is negative to the left of negative 3, positive to the right of negative 3 before 0 here, which means we have concave down and then concave up. Let's summarize this with some intervals. So we can say concave down occurs from negative infinity to negative 3, and then concave up occurs from negative 3 to 0. Of course, we have a vertical asymptote at 0. Now, sometimes concavity changes surrounding a vertical asymptote, but sometimes it does not. So actually, we should check the concavity to the right of 0. Remember, our function is still defined over there. We have a vertical asymptote at 0, but the domain does go beyond that to the right. So we could say it's concave up also to the right. Again, that would be testing like f double prime of 1 or something. We'll get a positive value there. So we have concave up also to the right, which means in our interval we'll also list 0 to infinity. So we can summarize our second derivative analysis with intervals over which our function is concave down, concave up, and then of course our inflection point, all coming from this second derivative. This will help when we put all of these characteristics now onto a final graph. If we move on now to try to put all of these aspects of this function on a graph, we'll start with the most basic items, which would include vertical asymptote and horizontal asymptote. So this function had a vertical asymptote really right on the y-axis, as seen above, and then it had a horizontal asymptote at y equals 1. So we'll have a horizontal line there. Now we'll also recall that above, as we've already listed, we have a local minimum or relative minimum at the point negative 2, 3/4. So I'm going to go ahead and plot that point. It would be at negative 2, 3/4, which is just below the horizontal asymptote that we have there. Furthermore, we have an inflection point at negative 3, 7/9, so that's even a little closer to the vertical asymptote, but still below it. And so those points we know exist. If we mark our concavity on the graph, we'll recall that it's concave down to the left of negative 3, concave up between negative 3 and 0, and then concave up to the right of 0 after the asymptote. So we have our concavity there marked as well. We could also mark the increasing, decreasing. We know it's decreasing to the left of negative 2. So I'll put a little arrow segment indicating that. It's increasing from negative 2 to 0. And then it's decreasing to the right of 0. So these characteristics have to show up with our final graph. Combining everything, we would have to conclude that if it's concave down to the left of negative 3, we know there's a valley or a minimum at negative 2. So we can kind of draw a little dipped valley segment there of our curve. But then the concavity changes at negative 3, which means it goes from all tangent lines being below it to all of a sudden them all being above it. So the concavity changes, which means now this inflection point is a little too close for comfort to my vertical asymptote. I'm going to just draw it a little bit lower so we can draw some more detail of this graph. In fact, I'm going to move the minimum value down a little bit too. We're just kind of estimating these, but I want to be able to show it visually. So we bottom out at negative 2 with a concave up kind of curve, but then the concavity changes at negative 3 to being concave down, and then it just chases. The whole point of an asymptote is that it chases it forever. So the limit of our function as x approaches negative infinity is this 1 value, which means our graph will chase the asymptote there forever. But if the concavity changes at negative 3, then we have to be able to see a clear change in trajectory there. It's hard to draw visually, but there is a change from being concave down to the left at negative 3 to being all of a sudden concave up. And then, of course, if the graph is increasing, we know it's going to chase this vertical asymptote going up forever. So it looks like our function actually passes through the horizontal asymptote, which is possible to do for a function. And then after, to the right of the asymptote, it's concave up everywhere, but it's decreasing. So according to what it should be doing, chasing the asymptotes, we could say our function probably has just one big branch that chases it upward toward the vertical asymptote and then out toward the horizontal asymptote. In summary, we could say our graph must look something like this. When graphing these by hand, of course, the whole point is to be accurate to the characteristics of the graph. It can be a little tricky to draw by hand every little nuance to the graph, especially around inflection points. But we want to make sure all characteristics are true to what we've drawn. Let's try a third example. This one is given as y equals x over the square root of x squared minus 1. That's our original function. We want to analyze and graph this thing. Of course, we'll want our derivatives to be able to utilize and analyze this one. So we could say here, using our derivative rules, which is plenty of work, I'm just summarizing the results here. This would be like a quotient rule derivative, all right? So y prime in this case would turn out to be negative 1 over x squared minus 1 to the 3/2 power. Again, there's a little work involved in getting that, but that's another video, another day. That's just quotient rule derivative here. And then y double prime, second derivative. Similarly, there's some work involved, but it should end up to be 3x over x squared minus 1 to the 5/2 power. Okay, and we can use these three equations to get everything we need for this problem. We want to analyze it and graph it. Now, as far as the domain goes, we look at our original function here. Given this original function, we cannot divide by 0, but nor can we take the even root of a negative. So there's a little bit of work in finding the domain in that algebraically, but it'll turn out to be anything from negative infinity to negative 1, but then union and skip over until negative 1 to infinity. So basically anything except negative 1 to positive 1 here for the other side. And that will be the domain that keeps all the algebraic rules in check. For our symmetry, again, this is where you test f of negative x. This function's symmetry turns out odd, and that's because f of negative x is negative f of x. That's the definition of an odd symmetry function, which means origin symmetry. So we'll see that when we look at the graph. If you consider x-intercepts or y-intercepts for this function, setting the respective variables to 0, you'll find that there actually is neither one here. So there's no x-intercept, there's no y-intercept. Now, in searching for asymptotes, this function actually has some interesting behaviors with it. So remember, for asymptotes, we take the limits as defined above. We recalled them above. So it turns out that for this function, the limit as x approaches positive infinity of our function, which involves a little work. Okay, if you go back to our chapter on limits, it's not a simple limit. This would be like, dividing by the highest power of the denominator to find this limit. But it turns out this limit as x approaches positive infinity is positive 1. But interestingly, if you take the limit as x approaches negative infinity, this will involve a different kind of trick where you have to fix the absolute value. We've seen that before. And this limit of our function will be negative 1. So interestingly, we have two different horizontal asymptotes. Those will have to show up on our graph. There are a couple of vertical asymptotes as well. This would be where the function is undefined. And of course, that would be where x is plus or minus 1. So really, we have two horizontal asymptotes as defined above and two vertical asymptotes. These will all come together on our graph eventually. If we move on to the first derivative, of course, in this case, we typically search for critical numbers. Searching for critical numbers, we'll look for where this first derivative is 0 or undefined. And in this case, given the way it's defined, we actually have neither that are not also excluded from the domain of the function. So we could say there's nothing where it's 0 and nowhere it's undefined. That is within the domain we've already listed, which means we have no critical numbers. Now, that doesn't mean there's nothing to consider. We could also recall that we have two vertical asymptotes. As we've seen in a previous example, it can make a lot of sense to put the vertical asymptotes down in this stage of our analysis. They're at -1 and +1. And what we'll find is that we can still test for increasing and decreasing surrounding the vertical asymptotes, even though they're not critical numbers. The first derivative to the left of -1 ends up negative, which means our function's decreasing. Between -1 and 1, remember the function is not even defined there. That's not in our domain, so we just kind of skip it. And then to the right of 1, we also get a negative first derivative value. So maybe finding like f prime of 2 or something to the right, we'll get that negative, which means our function is decreasing there. So we can say in summary, we have a decreasing function from -infinity to -1 and from 1 to +infinity, which means it is increasing nowhere. So our function never increases, and there are no local or relative extrema. So no local min or max. We can then move on to the second derivative. Remember, we're searching for inflection points or changes in concavity here. So we could test out, is the second derivative equal to 0 anywhere? And if so, that means there might be a change in concavity surrounding that. But it turns out that it's not. It doesn't equal 0 anywhere that's at least still in the domain. So we don't have to consider that. But again, that doesn't mean there's nothing to consider. We could still look surrounding the vertical asymptotes, kind of like we did with the first derivative. And at those vertical asymptotes, which of course are at -1 and +1, we will find we can still test for the concavity surrounding them. So like we could try f double prime of -2. If so, we'll find that that's negative, which means we have concave down to the left of -1. Remember, the function's not even defined in between those two vertical asymptotes. To the right, like f double prime of 1, we'll find that to be positive, so we could say concave up. And we should be able to take all this information now to the graph and put it all together. Looking at our graph, as you'll notice above, there's not a whole lot to put on it, but we do know that there are some vertical asymptotes. Those are about the only exciting things happening that we analyzed above. And we know that those occur when x is -1 or +1. We can place all of our asymptotes on the graph at once. Remember, we had 2 horizontal and 2 vertical, and they're all at 1s respectively, or -1s. And then if we understand also the concavity of our graph, we know it's decreasing and concave down to the left of -1. The only thing that fits with the concavity, the decreasing, and the asymptotes would be a branch in this lower left corner that just kind of chases each of those asymptotes as they go, and then nothing in between the asymptotes, and then to the right, in the upper right corner, a similar symmetric branch. Speaking of symmetry, remember that we have odd symmetry, which means this would be origin symmetry, or it could be considered like a bifold symmetry. If you fold vertically and then horizontally, this graph should land on itself, and that would actually match with what we have. So as you can see, it's good to put all characteristics analyzed above on the graph, and having them all gives more confidence that our graph actually is correct. Of course, you can use a graphing utility to check your work sometimes, but you may be asked at some point to graph without a calculator, in which case you'd have to be able to come up with all this stuff without looking at the picture ahead of time.